before everything, I want to say something about the midterm exam. So I think some of you are doing well on the midterm exam. I think that's great. And some of you might not do so well on the midterm exam. What I want to say is don't worry about it. Just try to continue working on the homework. And the design of the course is that before the midterm exam, basically we will cover, actually we have covered the fundamental structure for statistical mechanics. And the reason that we want to cover the basic stuff is because there's a reason for everything, okay? So at some point you might feel like when you try to apply statistical mechanics on different systems, it is quite machinery that you just follow a procedure. What I want to emphasize is that during half of the semester, we try to explain where this formalism came from. Okay, so it is really important to understand what is the basic assumption and how we came to the theory, such as the ensemble theory, and how to construct the corresponding ensemble and the partition function and the reason behind it. So the reason I said you don't need to worry too much is because now it's the second half of the semester. You still have some time. Try to figure out the concept you're not familiar with, or confused with. Try to talk, ask me. Okay. So that's basically what I want to say, because in the next half of the semester, we are basically going to apply statistical mechanics on the different situation. Okay, so I think that's the first thing I want to say. And the second thing is about the virtual classroom. It is basically because of the pandemic that I choose to take the virtual classroom in the following weeks. So I will send out the email notice if we tend to switch back to the real classroom. Okay. And I just realized that in order for you to unmute yourself, I need to click some setting. So in principle, at this moment, you should be able to unmute yourself if you have any questions. Okay, so don't hesitate, just interrupt me if you found anything is not really clear. Okay, so I think that's probably about it. So we should start today's lecture about the statistical mechanics. So as usual, we'll start from the review of the last lecture. So we kind of did a little bit motivation about the interacting free system. And the reason we want to understand it is because, as we know, in real world, in a material or in a physical system in your lab, basically the system are made of a bunch of microscopic interacting degrees of freedom. So in order to understand such a system, usually the first or the simplest approach is to assume that the system is like a non-interacting system. And the reason is that we need to start from some simple point such that we can understand the system. And then we try to add more ingredients or try to put back some energetics such that this non-interacting system is more close to the real system. Okay, so that's why understanding the interacting free system is very important, because it's basically the starting point of our system. Okay, so as I mentioned, when we try to analyze the problem, there are several steps. One is about the modeling. Okay, and this part contains basically identify the microscopic degree of freedom. Okay, what does that mean? It means like if you study the gas, the microscopic degrees of freedom should be the momentum and the coordinates of the particles. If you are studying a magnetic system, the microscopic degree of freedom will be the molecular magnetic moments or atomic magnetic moments sitting on each lattice side. Okay, and then once we identify the microscopic degree of freedom, we also want to specify what is the energy cost, or postulate the possible Hamiltonian for the microscopic degree of freedom. And the second step, after we did the modeling, what we need to do is we basically want to choose a suitable ensemble. And as I mentioned, most of the time we care about a system with fixed temperature. So the default choice is basically the canonical ensemble. Okay, and the next step is basically we try to calculate the partition function or calculate the observables. Here we calculate. And then and we make theoretical predictions to compare with the experiments. So basically, that's the step that we will go through when we try to apply statistical mechanics on a system. And usually, after we did some prediction and compare with the experiments, we need to modify our understanding about what are the microscopic degrees of freedom and what are the corresponding Hamiltonian. Okay. And also we mentioned there are several potential obstacles. One is about the modeling is usually non-trivial. And the reason it is not a trivial task to do the modeling is simply most of the time we will not have the microscopic resolution about the macroscopic world. Sometimes we can use some indirect probe to get some feeling about what are the microscopic degrees of freedom and what they are doing, but usually it is not the case. Okay, but because we are discussing about statistical mechanics, usually we will neglect the difficulties at this part because it requires specific discussion, depends on what kind of system you are discussing. If you are working with fluid dynamics, you need to discuss the property of the fluid. And if you are discussing about the solid state physics, you need to discuss more detail about the material. Okay, but we will mention some of the important details when we discuss the following subjects. And the second difficulty is at the part that we claim that we are able to calculate the partition function. Usually we can formally write it down, but as we have learned that we need to sum over all possible microscopic configurations. So usually we are dealing with an infinite series or an integral. And only very special cases, we are able to find a way to perform the integral or the infinite series exactly. So here, usually we cannot solve the partition function. And the reason is, as I mentioned, we usually need a specific form for our spectrum, or we need to have the very strong assumption that the system is non-interacting. Okay. Let me. So here, one of the very important assumption is the non-interacting assumption. As we have demonstrated in the last lecture, this non-interacting assumption actually simplified the task significantly by making the partition function factorizable. So instead of really calculate the high dimensional integral where these microscopic degrees of freedom couple with each other, when there's non-interacting, when there's no interaction, and you are able to factorize your expression such that you can calculate the partition function of each degrees of freedom one by one. And the four partition function will be the product of these individual partition functions. So that provides us a very helpful structure such that to calculate the total partition function, all we need is to understand the single particle physics clearly. Okay, and then we discussed the classical oscillators in the last lecture, where the partition function can be written in this way. Here we just integrate over all the microscopic configurations. And because we are working on the assumption that temperature is fixed, so we pick the canonical ensemble where the partition function is just the integral of the Boltzmann factor, which is minus beta times the total energy. Since we have n oscillators, the energy is basically the sum of individual oscillators. Okay. And here, beta is just the inverse of KBT. So as we can recognize, this integral is just a bunch of Gaussian integral that we are familiar with. And because it is interacting free, the partition function can be factorized by a bunch of single particle partition function, but raised to the power of n. And this single particle partition function is basically performed by, can be got by performing the Gaussian integral. And this thing will look like. And here, omega naught is the characteristic frequency for this classical oscillator. It's basically kappa divided by m, where kappa is the force constant of the spring or the restoring force. Okay, so now it is quite standard to notice that the expectation value of the Hamiltonian, which correspond to the internal energy of our system, can be derived by taking derivative of the natural log z with respect to minus beta. And you can just perform the derivation. And in our last lecture, we derive it to be n times kBt. And the specific heat is the derivative of the internal energy with respect to the temperature is just nkb. And here we are considering a 1D oscillator. So momentum and the position are not a vector. Instead, it's just real numbers. Okay. So the generalization of this argument or this analysis to a three-dimensional classical oscillator is also simple. You can try to perform that. And what you will found is the three-dimensional, the specific heat for the three-dimensional oscillator will be n times 3 kb. Okay. So in our last lecture, we try to discuss that from a more general scope. So we introduced the idea of equipartition theorem. Okay. In short, whenever you have some, energy, or in your Hamiltonian, you contains some term like x squared or momentum squared, then each one of these terms will give you contribution kBt divided by 2 in energy. So in specific heat, it will just give you kB divided by 2. So in the 1D simple harmonic oscillator, we have our energy described by kinetic energy and the restoring force given by the potential. And the kinetic energy contribute p squared, and the restoring force of the potential give us r squared, which will give us 2 unit of Kb divided by 2 in specific heat. So that gives us the specific heat for each oscillator is Kb. And if we have n of them, we will just have nkb. Okay. So for 3D free particle, basically that's the ideal gas model. We have the momentum square in 3 direction sum up together to be the kinetic energy of our system. So the mass and the constant in the front is not really important, as we have shown that in equipartition theorem, what is the characteristics frequencies is not important. So directly from the form of the Hamiltonian of the free particles, we know the specific heat should be n particles, and each one particle contains 3 quadratic terms, and each term contribute Kb divided by 2. So we got this 3 Kb divided by 2 contribution in our ideal gas calculation. So here's the calculation for classical systems. Are there any questions so far? Okay. So if not, I will continue review what we have done in the last lecture. So in our last lecture, we try to generalize the discussion to the quantum oscillator case. Okay. So we basically consider this is an ugly oscillator, but I think it did make the point. So basically we consider we have n quantum oscillators. Let's label by I from 1 to n. Okay. And we assume that every oscillator basically has the same characteristic frequency. So the energy spectrum for each oscillator is a function of n. And here, n basically is the label for the eigenvalue. And the energy, according to quantum mechanics, we know it is n plus 1/2 times h bar omega. And this omega is basically the characteristic frequency that's familiar to all of us. And the only important difference when we try to promote the classical analysis to the quantum system is now we have quantized the energy. And also we have quantum fluctuations such that the lowest energy is not 0. Instead, we have 1/2 h bar omega. But this constant will not play important role in the following analysis. But we just need to keep that in mind. Okay. So in our last lecture, we basically construct the partition function of the oscillator by summing over all the n's ranging from 0 to infinite with the Boltzmann factor exponential minus beta times the total energy, which is let's say okay. So as we mentioned, because each mode is not really coupled with each other, so this summation can be factorized into products of individual partition functions. So here we have done that with this zeta is related to an infinite series. So we just sum this infinite geometric series. Okay, and that's the expression for zeta. So once we know the expression for zeta, then we know the expression of our partition function, and the natural log of the partition function is just n times natural log zeta. Oops. So following the standard procedure, the internal energy is the expectation value of the Hamiltonian. It's just partial natural log z, partial minus beta. And you will find it to be an h bar omega times 1/2 plus 1 over exponential beta h bar omega minus 1. Okay. And this expression here is actually the distribution for bosonic mode. So that's the Bose factor at beta h bar omega. So here fb of x is defined to be exponential x minus 1 inverse. Okay. So here there's a kind of convenient way to understand this expression. So basically we have n such harmonic oscillator, and the harmonic oscillator has the energy h bar omega times 1/2 plus the occupation number n for that particular oscillator. But when you do the statistical average of this quantity, you'll find that the average occupation number is actually this Bose statistics function. Okay. So once we derive this expression for the internal energy, we can immediately try to calculate the specific heat, and eventually we get this particular expression. Okay. So this expression is somehow quite physical because we can try to ask what is the behavior of the specific heat at the extreme limits. One limit is that when the kPt is much larger than the energy scale of the oscillator, what does that mean? It just means that the system is more like a classical system, because now the fluctuation of the energy is so high that the gap of the energy gap of the quantum oscillator is almost unnoticeable under this kind of thermal fluctuation. So we should expect it to behave like a classical oscillator. So at this limit, basically beta h bar omega is approaching 0. So the exponential factor, exponential beta h bar omega, can be approximated by 1 plus beta h bar omega. Okay, which means that this exponential factor is very close to 1. Okay, so if you make this experiment in the specific heat, what you will find is this specific heat goes like nkb times beta h bar omega squared times okay, and you can notice that basically the beta h bar omega squared basically cancel each other, and this approximation is almost like nkb. So this consists with our understanding of the classical oscillator we just derived, because yeah, it is just the classical value we got. Okay, so let's consider another limit. When temperature is very small compared with h bar omega, what will happen? So when this happens, it means beta h bar omega goes to infinite. So in the expression for the specific heat, the most important contribution came from these exponential factors. And because beta h bar omega is huge, the exponential of it is also huge. So whether you subtract 1 or not is not really important. So what you will find is the specific heat is approximately nkb times the exponential decay factor. And because as we assumed, this beta h bar omega is huge, the exponential factor will basically kill everything, and the C, or the specific heat, will go to 0 very quickly. So this exponential factor tells us that the specific heat decays rapidly when kBt is about h bar omega. So if I make a plot, this is C divided by KB. And this is the temperature divided by TE. And here, this TE is H bar omega divided by KB, which is the characteristic temperature. And we call it TE because this model is related to Einstein. So this is the Einstein model for Phonon. Okay. So suppose the TE is somewhere here. Then here's 1. And basically it's very small. And then after the temperature is much higher than this TE, the specific heat is approaching NKB. And whenever it is smaller than TE, it basically decays to 0 pretty fast. So this is the Einstein model. And the reference is okay. So here we are discussing about the one-dimensional system, but it is relatively straightforward to generalize this to 3D system. The tiny modification to 3D is you will need to sum over 3 directions. And the occupation is still same basically. And then your partition function will have the product of these 3 different directions. And of course, because there's no interaction between them, you just raise it to the power of n. So during the calculation, if you assume that the 3 direction is basically identical, you will find your energy to be a proportion of 3 and stuff. And these 3 basically came from the 3 dimension. Okay. So we just went through the gist of Einstein model, and the important point for that is first, there's a very crude assumption that the Einstein model contains only a single mode. That is, we assume all the frequency of these little oscillators to be the same. They are just kappa divided by m. Okay. And the second thing that we should emphasize is that this is maybe one of the earliest work to introduce quantum mechanics into solid-state systems. To some extent, it is highly non-trivial because this paper is published at 1907, and the Schrödinger equation is published at 1925. Okay, so somehow, like always, Einstein postulates something before people have a clue about what it looks like. So that's basically Einstein's model. It's just a single mode approximation, but this is a very naive model for the real solid. So here I'm just going to describe what the phonon spectrum looks like in the usual case. Okay. So before anything, let me just draw a very simple lattice structure. Okay. So this is a ugly lattice where we can see that there are some atoms and they are arranged in a cubic lattice and they are interact with each other through some Coulomb interaction. So what we are trying to discuss is the concept of phonon. It basically is a mode for a collection of these atoms when they are oscillating. So basically, they'll jiggle around as if they are tied with each other by a spring. Okay, so if you look at the solid state textbook, you will usually find this kind of dispersion plot. Okay, we'll describe what is the meaning of these coordinates later, but I'll just write down or draw the picture about what it looks like. Okay, so usually we will see this kind of plot, and people say the lower branch is called acoustic phonon, and the upper branch is called the optical phonon. Okay. Something is quite obscure is what is this K? I'll describe that a little bit later. But what I want to say is that, you know, like in the previous case, we discussed Einstein's, where we assume that there's only a single mode. So the single mode approximation is almost like assuming the EK to be flat. That is basically the frequency or the energy of each mode is independent of this parameter K. So to some extent, Einstein's model is a very good approximation for the optical phonon. If we neglect the detailed structure, that there's some kind of energy dispersion within a small energy window. So in other words, when the temperature is low, actually the most important contribution is not coming from the optical phonon. Instead, we should try to understand the acoustic phonon, that is from this lower branch, because the energy of this branch is lower, which means that when we try to calculate the Boltzmann factor, this E is smaller, which means it plays more dominant role in the partition function and in the free energy. So we will continue our discussion in the next lecture by first understanding about what is this K, and we'll try to generalize our understanding of this quantum oscillator to the more evolved case when the frequency has some K dependence. Okay, so we will take a 10 minutes break. If you have any question, please just unmute yourself and ask me. Thank you. Okay, so I think we will continue our lecture. So as I mentioned, if you look at the solid state physics textbook, usually you will find this plot for Phonon. So what we can learn from this plot is there's a parameter K. We don't know what that is yet, but the energy will be a function of this parameter K. Okay, and as we mentioned, there are two modes. One is the optical phonon, and the other is the acoustic phonon. In most cases, that's the general setting. But in our discussion later, we will basically focus on the physics of this acoustic phonon. So in a real system, the behavior of the acoustic phonon could be quite different. Depends on the detail of the material. It could have, some different quantitative different behavior. Maybe it increase slower as the energy increase slower as a function of K, or it increase faster as a function of K. So those different behavior usually is not generic. The most important thing, which is the generic feature for acoustic phonon, is that nearby the small K. So when K is small, A is the lattice constant. Basically, we can approximate the energy as a function of K, which is defined to be h bar times the frequency as a function of K. It's basically linear in K. So what I want to say is the important feature or the generic feature for the phonon mode actually is nearby the small K limit. So in this small K limit, usually it is a very good approximation to linearize the dispersion. So the energy will be just the velocity of this dispersion times K. So it is linear in K. So so why it has this generic feature actually is tied with a theorem called Goldstone theorem. I'm not going to discuss how to get this theorem, but I'll just tell you the conclusion of this important theorem. If the system has a continuous symmetry, and there is there's a spontaneous symmetry breaking. One will have Kepler's linear dispersive low energy mode. So this is a very, crude conclusion for this Goldstone theorem. Of course, there are more precise statement about the left generators of the symmetry, but for our purpose, it is not really important. The importance here is that we are discussing about a lattice, which means, oops. It is. We are discussing about lattice, which means that we have a bunch of atoms, and they arranged in a very regular periodic lattice-like structure in the solid. So this system has a discrete translation symmetry, TA, which means that the Hamiltonian of our system is the same after we shift the system by a unit lattice constant. Okay, but this system actually breaks a larger symmetry. The larger symmetry is basically a continuous translation symmetry. Which means that the Hamiltonian is basically the same after you do arbitrary shift of your system. So the discrete translation symmetry is only invariant when you shift a specific step of your system. So it basically is invariant only when you shift A. If you shift your system by 0.5 A, it's not going to be the identical system, because if you shift by 0.5 A, this particle move to here, and the red lattice is not really equivalent to the blue lattice. Okay, but if we try to think about the lattice system as a spontaneous symmetry breaking of continuous symmetry, which is the continuous translation symmetry, the Goldstone theorem tells us that there must be Kepler's linear dispersive mode, and that actually is the Phonon mode. Okay, so that's like a very general background, like why this scene looks linear. But there's another important thing that we haven't really discussed, is what is the meaning of this K. So now I'm going to have a very short introduction about what is K. Okay. So before we do the discussion about what is K, let's try to think about what kind of system we are thinking about. First, we are talking about the lattice. With lattice constant A, which means that we are studying a system like that. Okay. And in principle, if we are discussing about big pieces of material, we will have a finite boundary of our system. Sorry. And here we are discussing a simplified version. Just consider one dimension, because in principle we can discuss three-dimensional systems, but you will just look more ugly and more complicated. So let's just take the one-dimensional system to make the point. Okay. So usually it means that the system has a system size that's L. So the assumption is that because the system is periodic with unit A, so the system size I can consider to be n times the lattice constant if I have n atoms. Okay. So for this system, we have at least two length scale. One is the system size L, and the other is the spacing between these two atoms. So that's the two important length scale in our problem. Okay. So that's the basic setting of our system. Okay. So for the 1D system, at least from the free particle example of quantum mechanics, we know that if we have a box with length scale L, and we can try to consider it as a free particle, then we said that there are two types of boundary conditions. One is the open boundary condition, where the two end of the box is basically that the particle cannot really penetrate. But there's another type of boundary condition, which is called the periodic boundary condition. And basically, what we try to wrap up this one-dimensional box and try to connect the ends to the heads. So that's the periodic boundary condition. Okay. So it is still a system with length L. So in the free particle case, we said that the important physics or the physical observables are not sensitive to the boundary conditions. So we can choose the boundary condition according to our convenience. So if we try to think about this periodic boundary condition case, and also we assume that we know the important wave function, which is the eigenstates of the system, should be some kind of extended wave. then we immediately get interesting restriction. The first thing is that because it is some kind of wave, the wave function should be proportional with something like exponential ik times r, where this r is the coordinates or the position of our system. Okay. And the second thing is that because the system is periodic, so if I have a position that's labeled by r, it should be equivalent to the position r plus l, which means that, if you travel around this box by translate your system by L, because the period of the system is L, you must end at the same point. Okay. So with this restriction, you immediately get the conclusion that exponential IKR must be equivalent to exponential IK R plus L. And this thing is basically IKR times exponential IKL. Okay. So you immediately get the interesting constraint that exponential IKL must be equal to 1. Okay. And what does it tell us? It tells us that this K must be 2 pi divided by L times an arbitrary integer. And the reason is that if you put it back, this exponential IKL will just give you 1. Okay, so here we use the periodic boundary condition and the wave nature of our eigenstates to get a interesting concept, which is this wave vector K must be 2 pi divided by L times some arbitrary integer. Okay, so as I mentioned, we actually have 2 length scale. So here we use one of the length scale. The other important length scale is this lattice constant A. So let's see what this lattice constant A is doing. So as we mentioned, we have this discrete translation symmetry. Okay, so because they are all arranged in a very regular pattern, and there are lots of its friends. So the discrete translation symmetry tells us that the Hamiltonian should be the same after you make a shift in A. So it is almost saying that what happened at X should be equivalent to what happened at X plus A. So again, as we mentioned, we expect the wave function to have some kind of wave nature. So the eigenstate should be proportional to with something like exponential IQ times some coordinates X. Okay. So if we input this condition, run similar arguments as in the periodic boundary condition case, we immediately get the condition that exponential IQ times A must be equal to 1. So this length scale A also gives us some interesting wave vector like object Q, which is 2 pi divided by A times some integer m. Okay. So it is interesting to make analogy between these two. So the first thing, or the first derivation we got, is by imposing a periodic boundary condition by hand. And the second way, Q, is derived by noticing the discrete translation symmetry of our system. So why it is so important to mention these two cases, it's because we are trying to make analogy with the free particle system. So for the free particles, we have continuous translation symmetry. Which means that you have a particle, and this is the potential that this particle experiences. And basically this potential is a flat potential. So it has the continuous translation symmetry. And the kinetic energy is simply a squared divided by 2m. Okay. And the momentum is just h bar k. So now in our lattice system, we have discrete translation symmetry. Okay. So it turns out there's a very important theorem called Bloch theorem, which I'm not going to discuss about the details of it. But the important thing is that your energy might have some form, but the important thing that is different compared with the free particle is that now your wave vector k is going to be identified with k plus g. And this g is the reciprocal lattice constant, which is the q that we derived. So at this point, it is a bit not so obvious what that is. So let's try to think about what that is. So again, let's take this trigger. So if there's no periodic structure in our system, that is, if we have the continuous translation symmetry, then k is just simply the wave vector that we are familiar with. And now, if we are consider a box instead of a completely open infinite wide box, then we realize that k needs to be quantized. That is, oops, we have 0, and quantized k is discrete by this delta k, 2 pi divided by L, and you will have a bunch of them. Okay, so it is the case when you try to go from the continuous translation system, but you constrain your system in a box of size L. So now you impose another condition that your system has periodicity A. And what you realize is that there's an important characteristic wave vector is related by 2 pi divided by A. Okay, so there's minus 2 pi divided by A. And the block theorem tells us that K should be identified with K plus G, which is this Q vector 2 pi divided by A times some integer, as we discussed here. Then what you realize is that suppose you have a K here. It should be equivalent to this K prime, which is K plus 2 pi divided by A. So that's the condition imposed by the periodic potential. And that also suggests, in order to describe the physics in this whole wave vector axis K, what you really need is actually the information between minus pi divided by A to pi divided by A. And this region is what people call the first Brillouin zone. Okay. Shorthand is this is BC. The reason is simple, because what happened here should be representable by what happened in this particular K. Okay. So at this point, it might look a bit confusing because we know K is related to something like 2 pi divided by the wavelength of this mode, lambda K. So if we set K is to some extent equivalent to K plus G, does that mean this mode has some wavelength lambda K plus G and lambda K equal to lambda K plus G? And it turns out it is a bit not so easy to understand why it is so, and it is related to the concept of wave aliasing. And the idea is simple. Suppose you have some wave that maybe have some wavelength, and you have another, let's use this as the, let's denote it as the wave with wave vector K. And we can try to describe the wave with wavelength K prime, which is K plus G or something. Okay. So it turns out, even though these two waves have different wave vector in real space, which means they correspond to different wavelengths. But if you just look at the discrete lattice site, you found the information you got actually is completely identical, because at this particular lattice position, those two wave actually has the same amplitude. So this behavior of wave alliancing basically is saying that if you have the continuous resolution of your wave, basically you can distinguish these two wave by their wavelength. But if you try to describe those two different waves only at some discrete points, you lose the ability to distinguish them. That's basically where this G came from and what this reciprocal lattice is doing. Okay, so now we roughly have an idea about what this K is. To some extent, it is just the wave vector to label the corresponding modes of our phonon. But we need to be careful because we are describing a lattice system with discrete translation or symmetry. So this wave vector is not like the conventional wave vector we are familiar with in the free system. Instead, it has this particular identical relation built by this reciprocal lattice vector. Okay, so that's a little bit detour about the concept of Brillouin zone, but we somehow need this concept in order to make sense for this plot. So now we know what this plot means is that you have some kind of oscillation frequency, and this frequency is identified by the corresponding wave vector K. And for acoustic phonon, it will correspond to a particular energy. And for the optical phonon, at the same K, you will have a different oscillation pattern, and that will correspond to a different energy for the optical phonon. So if we look at the plot where we try to describe this acoustic phonon, basically, if we have a box of length scale L, this dispersion relation is basically described by a bunch of modes, and these modes are different with each other, with delta K equal to 2 pi divided by L. So when your system size L is really large, all these discrete points are going to sit very closely with each other. That's why usually when you look at the phonon modes plot, usually they plot lines instead of dots. Okay. So why do we try to detour to this acoustic phonon discussion? Because in the previous case, we consider the Einstein model where we have the harmonic oscillator to be at the same frequency. So in order to describe the acoustic phonon, all we need to do is to make a very tiny modification about Einstein's result by noticing that in the Einstein result, we just assume single mode. Now, in order to capture the physics of acoustic phonon, what we need to do is to put in the wave vector dependence about the frequency of the oscillator. And we will treat each mode as if it is an independent oscillator. So these and all these tiny dots are represented by a quantum simple harmonic oscillator. Okay, so I'll just pause here